turn my system on, I'm getting pretty much an immediate temperature rise. The only time I don't do that is first thing in the morning when I first fire this up. And the most I'm getting is about 40 seconds. But it's taken about 2 hours and 45 minutes to get to its top temperature. So I've got a tea that is huge. Is this normal? I mean,
yeah, your reaction curve. So why? So what is your range? It's like a.
depending on what room temperature is, I'm getting up to about 98 degrees.
98?
Yeah, room temperature can be anywhere between 60 and 65 degrees in the morning. And I'm getting up to 98 degrees.
Oh, 98. So the range is 30 degrees something.
Yeah.
Okay.
So can I share something?
Well, let me do this. In your case, I will help you with this. You will draw a line like this, because I was figuring out. I was thinking it's really take you too long to reach the peak. So instead, you will mathematically draw a line, and that will be your T. Instead of T happening here, T is the sharpest curve, the steep, you will draw a line where your rate of temperature going up is at the steep, the highest rate. You draw a line at the highest rate and find the T that way.
Yeah, but I still have to sit there for another 3 hours and watch it. You know?
Yeah.
I mean, I graphed out the other things.
I would say there will be a period of time the temperature goes faster than other time, right?
Yeah.
Yeah, just measure that. Just measure that period of time. The temperature rise is fastest, the quickest. And use that, draw a line, and find the T that way. Let me explain a little bit. So if I understand correctly, yours is like this. It reaches, it takes 3 hours.
Yeah, I mean, even the short test we did where we just had P going, you know, I'm looking at 15, 20 minutes for that thing to level out, you know. And when I was doing the range, like I said, it took 2 hours and 45 minutes. That was the shortest time I did.
I think that's a common question. So yes, that's a common. So what I would suggest is just find where the temperature rise the sharpest. Find that period of time, and did some measurement like 30 minutes, like 35 minutes, and measure that temperature. And draw a line, and that will be range, and that will be your T. Instead of the T go 3 hours, you use this as T.
Okay.
So that was actually the author. Thank you for that question. So actual T is not because it never reaches. It will take really long. But like you said, the speed is very slow at first, and the speed is really slow at the end. Right in the middle, the speed is fast. Use that to find the T.
Okay. And where should I cut off from L? You know, where's that?
L is also here. L is so once you have this line established, that's where you start. That is a L.
Because I get, when I turn my system on, like it'll just be at room temp, and then as soon as the relay comes on, I get a half-degree
Start moving,
jump.
right? Yeah, start moving. Okay, if that's the case, you'll find L using the same line. That will be L. Instead of L started from here, L started from here. That's L. Do not do it in L because that's kind of random because it's hard to find L that way. You find L using this the sharp curve, the tangent curve. So when you're controller doing this, you find this curve, and this will be L. This will be T.
I have a question as well. So to clarify, the L, is that the time when it starts responding?
Yeah, start responding. But
Okay.
just like it's very hard to know where exactly start responding. So instead of this I'm sure once we establish this tangent line, and the L will be, that's room temperature. So this will be the L. When we turn it on, we don't find the L here or here. You have doubt where the L actually started, where is the L. But once you have this tangent line, that L is obvious. And
so the L, so when you're measuring the L, though, you're still probably going to see a little bit of a temperature increase, but it's not going to be much.
Yeah, actually that L is the temperature is already going up here.
It's going to increase, but not very much. But then you're going to see that sharp incline.
Sharp incline, yes. That is what we want to observe, that sharp incline, yes.
Okay.
Also, the PID tuning is not a accurate science. It's experience. It's and also it's very tolerant. So it doesn't matter you have 10% error or 50% error even. So it's a very, so the PID parameter is not even though it's off by 50%, we still have very good response. Only the difficult part is finding the optimum response. If we want to find the optimum response, then that became a lot of involved. If we just want to get the PID controller to get some good results, that's why PID controller is so popular, because the tuning portion is relatively tolerant to errors.
So I'd like to share something. I want to get your thoughts on it.
Mm-hmm.
I made some graphs with the with my tuning yesterday. Let me see. Oh, I need your permission to share.
Okay, yeah. Okay, now I can share.
All right. So, can you see the spreadsheet?
Yes. Wow, that's nice. Nice S curve.
Okay, so this one here is just when I adjusted the P only, and there's really not much of a, like the line is here, right? But there's really not much of an L there that I can see. Here in the PI and the PID, there was, like you can clearly see this here, and then you've got a steady increase.
Did everybody see the shell? I lost that shell shared.
I can see it.
Can see it? Why can I cannot see it?
Yeah, I can see it as well.
Oh, now I see it. Okay.
Oh, like I was saying, for the P, it's kind of just steady. Like there really wasn't any L time. For the PI and for the PID, there was, which is right here within the first 100 seconds for this one, and for the PID was within the first, we'll say 150 seconds. and then it was pretty steady increase, and then it tapered off here at the end. Like I guess my question is for this P part, how do I find my L for that?
I didn't know, but based on when I was tuning, it's all depend on if that light bulb is cold and hot. I would assume maybe if your light bulb is completely cold, your P curve will look like a PI also.
Okay. I think I'll try that again right now. Actually, I'll
yeah,
try
that delay is basically caused by physics because your light bulb everything need take some time for that 20 watts or 10 watts heater to actually start kicking in to have some effects. There's always a delay, but if your P do not have delays, maybe it's already warmed up.
Yeah, I think that's it. I hope that's it. That would be nice.
That's the problem I'm having because the glass on my bulb is so thick that once it gets hot, it stays hot all day long. Even if I turn the power off, you can still feel it that it's.
Yeah, that's probably give some practical experience. That is when we tune in the PID controller, we start with a cold one.
Okay, because
everything is already heated up. That is not the delay will not affecting represent the actual process. So we want to find the actual process where we started with cold, everything cold.
Okay, so I should probably redo my P then and just set the parameters to that with a cold, basically like a cold start, I guess, right?
Yeah.
Okay.
So that look like a nice S curve, and so you can find T's and L's once you get that S curve.
Okay. And then for the P, the value is the 1.2, right? 1.2 times whatever my T and L.
Yes, I have it on this paper. Yes, yep. That's the mass, all the mass inside. In order to find the P, I, and D.
Okay, and so that's going to give us optimal parameters.
That is not the optimal. That is just a start. That's the guidance.
Okay.
So this came from experience. This number all came from. This is proposed by two engineers maybe 50 years ago, and it's still widely used because it gave you a very good starting point.
Oh, okay.
It's not optimum or anything. It's just what the guidance. That's where you start to tune your PID controller.
Okay.
The final results depend on what happens in the field. You will observe your process. You will fine tune it a little bit. That's why they pay you $50 an hour. Is that right? Is that Joe? You got?
I'm not making that.
All right.
I hope to.
Yeah, that would be nice. Yeah, that's where you start, and then you observe the process with some experience. You know where to fine tune it.
Okay, so ideally we would want it to kind of heat up pretty quickly and then get to our set point. Kind of.
Yeah, that's another completely different subject where we want the speed. Yeah, how to get it quick, yes, fast. For the PID controller, it's 95% of time it works in the industry. 95%. For the other 5%, there's a higher demand. The PID may not get the job done. You may need a better, more sophisticated control system. But the majority of the industrial process, PIDs get the job done, yes. We actually have a graduate. That graduate works in Kansas City. The company is called Ascent Control. So we actually went to their company, Ascent Control, and went to their big big prototyping place. Our graduates, I'm so proud of him. This graduate is the engineer who programmed all the control system. There's so many controls. That is a GM, General Motor Assembly line, for their latest model pickup truck assembly in Mexico. So they actually put the assembly line, all the control is programmed by our graduates. There are so many big motors, they are PID controlled. And so many things going on the assembly line, all the control. And what they did is they will fine-tune everything. When everything is done, they disassemble it and ship it to Mexico. And that became the production line for the GM truck. I hope we have that field trips for our class. That year is really a good field trip because we really got to know what have going on in the industry and what our graduates were capable of doing.
Okay, so for the last part, I just want to make sure I've got it right because I don't want to have to email you and ask you later. For the last part of the lab report, tuning with the reaction curve, we'll do this math, and then once we get these parameters with our numbers from our PID tuning and stuff, what then? Right, we're like you got for P, you got 56 for your band, you got 222, and then you got 180. So
yeah,
we're gonna
just put it on the PID controller and watch it and compare with the auto tuning results. Yeah.
Okay, and then I mean, do you want us to continue trying to tune it, or are we just gonna look at compare those two results and that's it?
That will probably up to you, but yeah, all the after we got that guidance, that's the end of this
Okay.
lab exercise. But obviously, if you want to fine tune it even better, you will reference last week's lab, because last week's lab you know what P will do, what I will do, what D will do to the process. And if you observe the process, you find some problem you need to improve, you will look back to last week's lab exercise, that kind of experience you gained from last week, you can fine-tune these results.
Okay. Is there a certain, is there like a minimum length for the lab report?
No, like I always said, this lab report is not just written for me, it's written probably for yourself also. So just whatever thing you consider you learned worth putting on the paper.
Okay.
Yeah. That is actually why we write a report. It's not because we want to get an A for a grade. Is that right? We want to record the knowledge.
I think I'm done with my questions.
we want to record the knowledge we gained.
Yeah.
All right, excellent questions. You guys all ask good questions. I felt it helps me and it helps your peers also. So I will see you guys next semester if we still not yet. If any of you graduating, congratulate. Otherwise, I'll see you next semester.
Are you? What classes are you teaching next semester?
Next semester, I'm teaching my favorite class. I have another favorite class I teach. It's called 422. It's power electronics.
Okay. I'm taking that one and I'm taking 482, so I will see you next semester.
Yeah, I'm not teaching 482. 482 probably will be somebody else. I will teach 422.
Yeah, I've got that one.
Yeah, that is a very practical class because that will dealt with everything happens today, like green energy, the electric cars, power electronics. That area has seen amazing growth in past 20, 30 years.
All right. Well, see you next
And
semester.
hopefully after that class, everybody build an electric car.
Well, thank you.
Yeah, that will be a great project.
I have one. I have my Raspberry Pi car.
Oh, you already have one. Wow. Jim, you're always ahead of the curve.
Yeah.
Okay. Thank you, guys. And I'll see you hopefully in person next spring sometime.
All right.
You
All right. See you.
Mhm.